Hello, my name is Kyle McClintick, and thank you for giving me the opportunity to be a part of this reproduction conference. The title of my work is Reproduction of Evaluating Adversarial Evasion Attacks in the Context of Wireless Communications and Convolutional Radio Modulation Recognition Networks. So to clarify, I am doing the way I stumbled into this conference is I am actually doing uh, some novel work in the area of adversarial perturbations in over-the-air scenarios, which is the topic of the first paper in this title. So in doing that work, I've been reproducing the first titled work as a benchmark. And the second work in this title is the machine learning work that features a data set and supervised learning model that is used to craft and evaluate adversarial perturbations in the first paper. So this is the threat model of the adversarial perturbation paper that I recreated. So they have three players in this threat model. They have a transmitter, an eavesdropper, and a receiver. So the transmitter and receiver are working together to send a message and decode it and hopefully get a good bit error rate. And then the eavesdropper is receiving on an independent but identical distribution of the same wireless channel. And they are trying to classify the modulation class of the observed time slices of the signal to one of 11 modulation classes. So it's a convolutional neural network that is trained, I'm assuming it's trained over the air, trained live. So there's no difference between training and testing sets. And we've assumed that the transmitter has stolen that trained CNN model, and they are crafting white box attacks, specifically FGSM attacks from that stolen model. So the way that they do that is they compute the gradient of the predictions of the stolen model with respect to pre-transmission inputs. So these are very clean inputs. There's no channel, there's no noise applied yet. And the idea is that by making small changes to the amplitudes of each sample of the signal, it will disrupt the fragile classifier while not disrupting the communication chain too much. So in recreating the just the bare classification paper, we trained the classifier. And something that a lot of people have noticed is even when there's very little noise, because they have the data set that they use has a sortable signal to noise ratio for the AWGN aspect of the wireless channel. So what I've done here is I've evaluated the trained model on just the lowest noise data, which is 18 dB SNR is how they compute it. And there are three pairs of classes that still have pretty poor classification accuracy, as you can see in this confusion matrix here. So I wanted to know why that is. So what we found, the answer to that is there's not enough symbols in each of these time slices. So there are 128 sample time slices at 8 samples per symbol. And these are the three pairs horizontally kind of aligned here. These are the three pairs of modulation classes that, as you can see, look pretty similar. The two continuous schemes on the bottom we've plotted in the time domain, just the amplitude of the in-phase and quadrature components, whereas we've done a scatter plot for the other four. And there's a lot of similarity here. And we found that if we either decreased the samples per symbol from 8 down to something like 4 to 2, then more symbols were able to be in that 128 sample time slice. And we saw the classification at high SNR be correct. Alternatively, we also saw that happen if we increase the time slices to maybe 256 or 512 samples. So visually, you can just see why that multicollinearity issue was occurring. Something the adversarial perturbation paper claimed was that for the BPSK class, as you can see here, this pre-transmission BPSK signal, there's no phase offset, so the quadrature component is zero valued. It's just plus or minus in the in-phase component. So what the authors claimed was that since the CNN has no bias terms in the first layer, that if you give it zero valued inputs, you will get zero valued outputs, zero valued gradients, which will give you zero valued perturbations. So we found that to be true. The only way we could get non-zero perturbations, which would be the dashed line for the quadrature component, the red line, is if we either used a bias term, which caused a vanishing gradient problem and the model did not train well, which is also what the authors found, or if we use dither, and dither is just adding the smallest floating point possible plus minus to the signal, just to make sure it's not exactly zero valued inputs to the convolutional neural network. And then you get the non-zero gradient and you get the non-zero perturbation as visualized here. So that's something that we agreed with the authors on. An issue we found with the foundational classifying paper and dataset paper was that they defined the standard deviation of the AWN channel for the GNU radio dynamic channel model block they used. But it actually they defined the variance, but it actually takes the standard deviation. So they were missing a square root in their definition that they needed. And they additionally did not have the standard deviation because of the in-phase and quadrature components were separate. And the result was when we separated the signal from the noise and we computed the signal to noise ratio of the actual created signals, that there was about a 6 dB error in the signal to noise ratio, and the noise was actually not as high as they were reporting it, which is a significant issue for reproducing the paper. So we found that when we divided the standard deviation by 2, and when we used the standard deviation and not the variance for the GNU radio channel model, that we got the correct signal to noise ratio. So when we said we have 0 dB, it was actually 0 dB. When we have -20, it's actually -20, and so on and so forth. So finally, crafting some perturbations ourselves to try to match the perturbation paper. We have a bit of a mismatch, as you can see. So on the left, we have our reproduced result. On the right is the reported result. This is for the BPSK class only. The accuracy of the eavesdropper compared to the signal to noise ratio of the signals that are observed by the eavesdropper. So because the noise is different than reported, our curve is shifted to the side, as you can see if you compare our blue line to the red line. And the reason why I'm not comparing the blue line to the blue line is because the perturbation paper says that the symbol energy is 1, but that's actually a constraint that they had to enforce. In the original data set, the sample energy is 1. So the symbol energy is 8 at 8 samples per symbol. So as a result, the perturbation strength is weaker than intended. So that's why we have our strong 0 dB blue perturbation kind of following more of a shape as their red line, which is their weaker, moderate weakness, 12 dB displaying that kind of hump feature where the perturbation strength starts to become larger than the channel noise energy. So in my ongoing work, I learned a couple lessons here. To reduce the multicollinearity, I need to either have less samples per symbols. What we're using now is 2, or larger time slices. I do use dithering, but I've actually moved away from the BPSK class in favor of the QPSK class to showcase results because it's more representative of the 11 classes. Having this 0-valued quadrature is really specific to the 1 BPSK class, so I've decided to do away with that. I'm computing perturbation and noise ratios correctly, so things are easier to compare and more correct to compare. And I found that with machine learning, if there's an incorrect classification, it's important to be able to find out why that has occurred. So instead of in the original data set, they have a single multipath channel, they have a single carrier frequency offset, single symbol rate offset. And I've done what they've done with the AWGN, which is have a sortable range of values, some of which are 0 value. So I can remove maybe the carrier frequency offset from the data and say, okay, am I still getting an incorrect classification? And try to isolate different channel variables and find out why misclassifications are occurring. I think that's important to have. So to conclude, I agree with all the findings of the perturbation paper, and I found that there are a couple of issues with the original data set and CNN training paper that were not fully discussed in the perturbation paper, such that in trying to recreate the perturbation paper, I had some mismatches because those, while they corrected for those errors, they did so without communicating so in their paper. So thank you very much for listening. I really enjoyed reproducing both of these works. They both have had a tremendous impact on the wireless community, generating a lot of interest for adversarial perturbations. Machine learning security is really important right now, really important for us to investigate, to make sure that everybody is safe and everything works correctly. So thank you very much.